In this video, I'm going to discuss what's called the Copenhagen interpretation of quantum mechanics. A lot of the videos that will occupy the rest of this Foundations of Quantum Mechanics playlist are going to be about various interpretations of quantum mechanics. This one is about what's called the Copenhagen interpretation, which is seen as kind of the orthodox interpretation. And it has been since these two scientists back in the early and mid 20th century sort of pushed for this interpretation of quantum mechanics. And so Niels Bohr being kind of the leader of this movement, and Werner Heisenberg also being important in pushing this movement to accept the Copenhagen interpretation as the orthodox interpretation of quantum mechanics. In general, an interpretation of quantum mechanics, what we mean by that is we want to interpret what the wave function means. We've been talking about the kind of three big problems, I guess you could say, in quantum mechanics, which are the measurement problem, the ontology problem, and the locality problem. And so these interpretations are essentially saying, okay, we have this equation called the Schrodinger equation, and what we're looking for with the Schrodinger equation, since it's a differential equation, is a function called the wave function. And these wave functions are solutions to the Schrodinger equation, and some of them actually say something about the kind of predictions we can make in quantum mechanics. But there's still no interpretation about what the wave function actually means. So what in the physical world is it referring to or describing, and things like that. So these interpretations that we will be talking about are ways of trying to interpret it. And so, like I said, this is the Copenhagen interpretation, which is the sort of orthodox position in quantum mechanics interpretations. And so the way I'm going to formulate this is as essentially stemming from two axioms here. So Bohr and Heisenberg, or even Travis Norton, whose book I'm following for this playlist, none of them actually formulated it this way, but this is the way that I'm going to formulate it. And so the Copenhagen interpretation is predicated on two axioms. So there's one that I'm calling the Neo-Kantian axiom. And so this has two parts. And the first part is that humans must understand the world in terms of classical physics. And so if you know anything about Immanuel Kant's philosophy, and I actually have a playlist where I go over this if you are interested more in it. But one of the aspects of his philosophy is this idea that humans have a sort of experiential mode of interacting with the world, and this is called the phenomenon. And then there is the noumenal world, which is the world that humans don't have access to. And the reason for this dichotomy here is that when humans sense something, then their own mind sort of brings this thing to bear on it, which are the categories of understanding as well as things like space and time. And so we don't know that the noumenal world actually has those things, and there's no way we can know, because the only way we can understand the world is through those categories of understanding. And so this is what I kind of mean with the classical physics, where classical physics is sort of the way in which humans have to understand the external world. And then the other part of this is that quantum mechanics cannot be understood in terms of classical physics. And so quantum mechanics is sort of, in the Kantian sense of the word, it's noumenal. So it's something that we don't actually have access to, because we have to interpret the world with classical physics. Then the other axiom here is the axiom of logical positivism. And so this is essentially just the, I guess, main tenet of logical positivism, which was a philosophy in the early and mid 20th century that it wanted to sort of weed out as much of sort of metaphysical claims as possible and say that everything had to be empirical. And so you'll oftentimes even see it called like logical empiricism or empirical positivism or things like that, because it's very focused on the empirical. So what humans can do with their senses, what we can know using our senses. And so it has this principle that's essentially the only thing anyone can meaningfully talk or think about are those things which can be verified, where verification has to be done through the senses. And so only things that humans can actually experience or sense are things that we can meaningfully talk or think about. And anything else is therefore just metaphysical mumbo jumbo and a waste of time. And so it's not something that we should actually be spending time, trying to discuss about things that we can't see or measure or anything like that. We should only trust what can be sort of ascertained through the senses. And so because quantum mechanics is not something that a human can even conceive of in classical terms, which from the Neo-Kantian axiom says that we must understand the world in terms of classical physics. And so since quantum mechanics is not something that we can conceive of in classical terms, it is not something that can be verified. So because it's not something we can experience, it can't be verified. The reason we can't experience it is because it is not classical, and we have to understand the world in classical terms. So it is not something that can be verified, or at least whatever is happening to the quantum system when it is not being measured, which cannot by definition be verified since it is not being measured. So there's sort of no thing being probing the system, whether that's just us looking at it with our eyes or actually using some instrument. And so while we're not measuring it, then it's sort of not real. So that's what we mean here with the Copenhagen interpretation. So from this, we get what I think is the main thrust of the Copenhagen interpretation, and that is that the only thing real in quantum mechanics is what we see in our measurements. So what happens between those measurements is meaningless, or Bohr even goes so far as to say that it's not real. So it's not real what's happening between the measurements. So in classical physics, making a measurement has a negligible effect on the system being measured. In quantum mechanics, however, the act of measurement has unavoidable and enormous effects on the system. And so by the Neo-Kantian axiom above, it is categorically non-classical. So essentially saying that a necessary condition for something to be considered classical, and like classical physics, is that measurements have a negligible effect on the system being measured. And since that is not the case with quantum mechanics, that is one of the reasons why it is non-classical. And so as such, all we can know or verify about a quantum system is how it behaves when it is being measured. So using instruments that are described with classical physics and interpreted by humans. And so when we actually measure or probe these quantum systems, we're doing it with instruments that essentially translate it into some classical analog of the quantum system. We talked about the measurement problem in an earlier video where, we're measuring this quantum system and then we're looking at it with a classical system because, the pointer on our measuring device is going to be classical, and then it is also interpreted by humans. And so we're trying to understand it in classical terms, but it's not something that is classical, and so it's something that is just in principle and categorically outside of the human ability to understand. So since by definition we cannot measure a system that is not being measured, we can never know or verify anything about the unmeasured system. So by the logical positivist axiom from above, this means that any discussion about a quantum system that is not being measured, i.e. that is between measurements, when I called it in an earlier video, I said when it's in its sort of quote-unquote quantum state or superposed state. So when it's not being measured, we can't say anything meaningful about it. And so if we try to talk about what the wave function in a state of not being measured is, that's just nothing but metaphysical gobbledygook. And so as far as the wave-particle duality of quantum mechanics, Bohr thought that we ought not take this too seriously in any ontological sense, since these are classical descriptions being applied to quantum objects. Yet simultaneously, we do need to take this duality seriously in a more epistemological sense, since they allow us to understand the results of experiment. And so this wave-particle duality sort of comes out of the fact that this is what we observe in experiments. And so we have to take it seriously epistemologically in order to understand what these experiments are telling us. But we shouldn't take it seriously in any ontological sense, because this would be attempting to impose classical descriptions onto quantum systems. And so we have to, like I said, we have to take it seriously epistemologically, but not ontologically. All right, and so in this way, we should not try modifying these two contradictory and yet mutually exhaustive views of with any unverifiable theorizing. And so essentially we have this wave-particle duality, and so we shouldn't try to, say anything more about it than just that there is this wave-particle duality that lets us understand what our experiments are telling us. But we shouldn't try to add anything else onto it to sort of try to explain the wave-particle duality in some way that would make sense to beings that need to understand things in a classical sense. And so that is sort of what's meant by we shouldn't try modifying these two contradictory because something being a particle in a wave is not possible, at least not in the classical physics sense, which is the way we have to understand it. But they're mutually exhaustive, meaning that the wave and the particle duality is completely explains the system, at least in the sort of epistemological sense that Bohr and Heisenberg were often using. And in fact, Norson here, whose book I'm following for this playlist, actually says something about this. So he says, whatever exactly Bohr and his colleagues may have meant when they made claims implying the completeness of the quantum mechanical description, it is not exactly the same kind of thing that Einstein and Schrödinger meant by this same word, and against which their objections were made. For Bohr and other Copenhagenists, the completeness of quantum mechanics did not mean that the theory provides a literal and direct and exhaustive description of the physical states of external objects. Indeed, as we have seen, for Bohr, the essential lesson from quantum theory is precisely that such an exhaustive description is, for supposedly deep philosophical reasons, impossible to achieve and thus inappropriate to seek. And so that's kind of what I meant up here with this, not trying to modify it, that we shouldn't be looking for, more answers about, sort of why this weirdness happens, or trying to sort of reconcile it with classical notions of classical physics. It's the case that quantum systems are, in the Kantian sense, noumenal, and so it's not even appropriate for us to seek sort of noumenal explanations, because we can only ever have phenomenal descriptions. All right, so for Bohr, completeness is used instead in an epistemological or semantic sense rather than the realist or descriptive sense discussed before. So something less along the lines of no aspect of objective reality has been missed, and more along the lines of you can't rationally ask for anything more. So anything more than this formal refereeing between the complementary classical concepts such as waves and particles or position and momentum without lapsing into meaningless unscientific metaphysical talk. So, in other words, completeness means the complete set of things we can know, not the complete set of things that exist. And so, in a way, Bohr is almost agreeing with Einstein and Schrodinger here in saying that the wave function is just telling us something epistemological rather than ontological. Where he differs seems to be that Bohr is saying that we shouldn't try to square these, sort of contradictory things, such as wave particle duality and not having definite position and momentum, that we shouldn't try to square this with reality out there. Whereas Einstein and Schrodinger wanted to say, no, there has to be something in reality that, is missing in our wave function, but that we could, at least in principle, discover or explain. And Bohr is kind of saying, no, we can't. That's not possible. So you shouldn't even try. All right. So Norson actually quotes David Griffiths, whose textbook I've used in my standard quantum mechanics videos. He quotes him at length here on the sort of broadly speaking three positions taken by people in quantum mechanics. So I'll put part of the quote here. So suppose I do measure the position of the particle and I find it to be at some particular point C. Question: where was the particle just before I made the measurement? There are three plausible answers to this question. They serve to characterize the main schools of thought regarding quantum indeterminacy. So the first one is the realist position, which is, the position that people like Einstein and Schrodinger would have advocated for. And so this is say that the particle was at C, or, at least some finite distance away from C, but it was definitely at some place, you know, from which it would actually end up at C sort of in the next moment. So this certainly seems like a sensible response, and is the one Einstein advocated. Note, however, that if this is true, then quantum mechanics is an incomplete theory, since the particle really was at C, and yet quantum mechanics was unable to tell us so. To the realist, indeterminacy is not a fact of nature, but a reflection of our ignorance. Evidently, psi is not the whole story. Some additional information known as hidden variables is needed to provide a complete description of the particle. Then number two here is the orthodox position, which is kind of the one we've been talking about here, but we'll see that it's actually fairly related to the third position here, but Griffiths calls this the orthodox position. The particle wasn't really anywhere, and so that's kind of what we've been talking about, that before a measurement or between measurements, to even say something like, to even apply something like position or momentum to the particle is sort of meaningless, and so we shouldn't even bother talking about it or exploring what is meant by that, because it's not something that humans can even comprehend, since we have to comprehend things using a classical physics framework. So the orthodox position, the particle wasn't really anywhere. It was the act of measurement that forced the particle to take a stand, though how and why it decided on the point C we dare not ask. Jordan said it most starkly. Observations not only disturb what is to be measured, they produce it. We compel the particle to assume a definite position. This view, the so-called Copenhagen interpretation, is associated with Bohr and his followers. Among physicists, it has always been the most widely accepted position. Note, however, that if it is correct, there is something peculiar about the act of measurement, something that over half a century of debate has done precious little to illuminate. That goes back to the measurement problem video I made before. So the third position is what's called the agnostic position, which is just refuse to answer. So Griffith says this is not quite as silly as it sounds. After all, what sense can there be in making assertions about the status of the particle before a measurement, when the only way of knowing whether you were right is precisely to conduct a measurement, in which case what you get is no longer before the measurement. It is metaphysics in the pejorative sense of the word to worry about something that cannot by its nature be tested. Pauli said, one should no more rack one's brain about the problem of whether something one cannot know anything about exists all the same than about the ancient question of how many angels there are able to sit on the point of a needle. For decades, this was the fallback position, Griffith says, of most physicists. They'd try to sell you answer 2, but if you were persistent, they'd switch to 3 and terminate the conversation. So, in other words, both 1 and 2 make rather definite ontological claims, where the first one is that prior to the measurement, the particle really existed somewhere, or in the second answer, that it did not really exist anywhere. So, while 3 just sort of punts the question altogether. So I'm going to end here with a few quotes by Bohr and Heisenberg that Norson supplies in his book that kind of, highlight what their sort of thinking was on this subject. And so Heisenberg says, the idea of an objective real world whose smallest parts exist objectively in the same sense as stones or trees exist independently of whether or not we observe them is impossible. Then 3 of them here from Bohr. So, in a new light, the old truth that in our descriptions of nature, the purpose is not to disclose the real essence of the phenomena, but only to track down, so far as it is possible, relations between the manifold aspects of our experience. And so that kind of goes back to that Kantian axiom I mentioned above, where he's essentially saying that we shouldn't look for, he calls it the real essence of phenomena, but you could put that in Kantian terms as the noumena, but only track down so far as is possible relations between the manifold aspects of our experience. So that would be sort of the Kantian phenomena there. All right, then this next one, the entire formalism is to be considered as a tool for deriving predictions. So it's kind of that shut up and calculate mindset there of definite or statistical character as regards information obtainable under experimental conditions described in classical terms and specified by means of parameters entering into the algebraic or differential equations. These symbols themselves are not susceptible to pictorial representations. And then finally, there is no quantum world. There is only an abstract quantum physical description. It is wrong to think that the task of physics is to find how nature is. Physics concerns what we can say about nature. So again, that goes back to that thing about the only thing we can sort of meaningfully think or say about physics or nature or whatever you want to call it is stuff that humans can understand, and only in sort of a classical description, only in classical terms, and so and only on things that we are able to measure and then experience, experience whatever the readout of the measurement was. But anyway, that is essentially the Copenhagen interpretation of quantum mechanics, which, like I said, is kind of the orthodox position in quantum mechanics, and the thrust of it is what I have here in bold, so that the only thing real in quantum mechanics is what we see in our measurements. So what happens between those measurements is meaningless or even not real. And so that is, and the reason I included that Griffiths quote is because I like this idea of, when somebody talks about, their interpretation of quantum mechanics, they're probably going to sort of pay lip service to number two right here. But if you press them on it too much, they're just going to sort of go to number three right here, which is, you could almost say that that's actually probably the orthodox position there, number three, because that's really the shut up and calculate kind of position, where number two, as I said down here, does make some definite ontological claim, which is the claim that when something's not being measured, it doesn't really exist anywhere. And there actually has been philosophies that have sprung off of this, like agential realism and things like that, that really take this sort of Copenhagen interpretation of quantum mechanics seriously. And I think it's also kind of where a lot of the what they sometimes call quantum woo comes in, where people try to talk about quantum mechanics like it's this sort of magical thing, and that it's inexorably entwined with consciousness, and that humans sort of make the world, make their own world, and things like that. And so I think that this orthodox position has kind of done a bit of harm in that sense, but in a way it's almost a little bit intuitive, or at least when you're doing the math, like if you watch my math videos, it kind of doesn't come up that much. Having to interpret quantum mechanics in some way doesn't come up as often as you would think. Like when you're solving the Schrodinger equation for the hydrogen atom, a lot of times you start saying things like, there's more electron density here, and so that's kind of an interpretation, but it's still a very surface level interpretation, because you're not actually saying what it means that there's electron density here. And so when you're doing quantum mechanics, the fact that there's not a good interpretation of it doesn't really come up that much. The fact, whether quantum mechanics is a pilot wave, or if it's the many worlds interpretation is true or something like that, doesn't actually come up that often. I mean, you can see just the fact that the orthodox position has been this Copenhagen interpretation, and yet we've been able to use quantum mechanics for all kinds of great technology and inventions and things like that. So it actually hasn't been that big of a deal that we don't have a good interpretation of it. And so, and that's one of the things that somebody who takes the Copenhagen interpretation seriously, that somebody who does adhere to the orthodox position would say is the reason why Bohr was right, that it's sort of a waste of time to try and come up with a good interpretation of quantum mechanics. But anyway, I'm starting to ramble a little bit. I hope you found this video interesting, and I will see you in the next one.